All right, welcome back, folks. Let's go ahead and let's quickly review where we left off with yesterday, because I want to go ahead and finish up with this problem in a moment. So if you don't have this in front of you, if you don't have this work in front of you, let's go ahead and quickly pause the video. Go get the work that you submitted yesterday. And so yesterday, remember, I asked you to finish to do this here for this particular problem. I asked you to find the mole ratios. I asked you to calculate for the molar mass of hydrogen and the molar mass of ammonia, NH3, so that we can go ahead and do this particular problem. All right, so with that said, then go ahead and pause the video. If you don't have this in front of you, go ahead and go get it. And then once you come back, go ahead and unpause the video, and then we'll work out this problem together, okay? All right, so what we were doing yesterday is that we were trying to do a calculation, a type of calculation that allows us to compare, to allow us to determine the masses within a chemical reaction. Okay? And so the masses involved in a chemical reaction. So we were able to do what we've been able to do up until this point is we've been able to compare moles, we've been able to compare masses, the number of particles, molecules, and atoms, and so forth. Okay? And so what we were able to do that from the balanced equation. So if the amounts were, we could obtain those amounts from the balanced equation itself. So what we did yesterday, we talked about how we can obtain the mole ratios, and what we did from there is once we know what the mole ratios are, we were able to calculate for any changes to that would occur if we changed one of the components of the reaction. If we change the amount of one component of the reaction, what would happen to the other amounts of the other components of the reaction? Okay, what would happen to the amounts of the other components of the reaction? And so we did that with the moles. Okay, so which means then, for example, here the balanced equation gives us here then that we have 1 mole. So let's go ahead and get started with this one. Okay, the balanced equation then gives us here that we have 1 mole of nitrogen. When we reacted with that with 3 moles of hydrogen, we would get 2 moles of ammonia. So the 1, 3, and 2 here, the coefficients that we used to balance out this equation, allows us to determine the number of moles involved in this reaction as well. What does that mean? That means then, if let's say, for example, we start out with 1 mole of nitrogen, we would need then exactly 3 moles of hydrogen to get this reaction done. Now, the question then is, what if we did not have 1 mole? So remember, if there's no number written here, it's implied to be 1. Okay, let's say then if we didn't have 1 mole, but let's say we had half a mole. So we had less than a whole mole. Well, we would know then, in order for, what would happen then is that we would need less hydrogen. If we had less nitrogen, we would need less hydrogen to react with it. So that means if we only had half the amount here of nitrogen to start out with, we would only need half the amount here of hydrogen to start out with. Okay, so roughly that's how you want to go about doing this. Okay, and that's the idea behind these stoichiometric calculations that we've been doing. And so with that said, then we talked about how yesterday doing that calculation is very straightforward, very easy. The problem then is that we can't measure out moles. We don't have tools, we don't have measuring devices that allows us to measure out moles. And so we have to be able to convert these moles into masses. Okay? So then therefore, instead of 1 mole of nitrogen, what would be the molar mass of nitrogen that we would need to use up three moles here, or the mass equivalent to 3 moles of hydrogen here. So we have to do this mass to mass conversion. Okay, and so that's where we left off with yesterday. And so let's go ahead and look at this problem here, and let's talk about it. Okay, so in the problem that we were given here, we were told then to find the mass of ammonia here that would form if we started out with 5.4 grams of hydrogen. So the question is asking us, if we only have 5.40 grams of hydrogen to start out with, what would be the amount of ammonia that we would form if we ran this reaction? Okay? All right, so to do this, then what we need to do first is, let's go ahead and write out the mole ratios. Okay? Now, remember, I told you yesterday, you don't necessarily have to write out all the mole ratios. Hopefully, at some point, you'll be able to figure out which mole ratios to use. But just as practice here, let's go ahead, and I asked you to do this. So let's go ahead and write out the mole ratios here. first mole ratio here would be a comparison between the amount in moles of the two reactants. Okay, so we would have then 1 mole of nitrogen for every 3 moles of hydrogen. Okay, we could take the reciprocal of that as well. So I'll let you do that, but that's 1 mole ratio that we can derive. Okay, so that's 1. Okay, let's take a look at another one. Okay, how about nitrogen and ammonia? So we have 1 mole of nitrogen over 2 moles of ammonia. And again, we can take the reciprocal of that one to form another mole ratio. Okay, so we have that mole ratio as well. And then finally, the mole ratio that compares hydrogen to ammonia. So we have the 3 moles of hydrogen for every 2 moles of ammonia. Okay, and again, take the reciprocal. Okay. All right, so those are the 3, what we refer to as 3 unique mole ratios, because they compare 2 different components of the reaction. And then the reciprocal of those, we can take the reciprocal of those to form the other 3 mole ratios. Okay. All right. Let's go ahead then and let's answer the second question I left you with. What is the molar mass of hydrogen? Well, the molar mass of hydrogen, remember, is the mass of 2 atoms of hydrogen, which is going to be 2 grams of hydrogen for every 1 mole of hydrogen. Okay, so that is the molar mass of hydrogen. And then finally, the molar mass of nitrogen, ammonia, that would be 1 nitrogen and 3 hydrogens, which would give us 17 grams of ammonia for every 1 mole of ammonia. And we learned, and so if you can't remember where we got these numbers from, look back in chapter 10 where we did molar masses, or come by and see me and get some help with that. Okay? All right, so those that's what I asked you to do at the end of class yesterday. And so why do we need this? Well, this is needed in order to do this reaction, do this calculation here. Okay, so let's go ahead and let's set up this calculation and let's work it out. Okay, all right, let's go ahead then, and this calculation then involves a conversion. And remember, I told you it involves 3 separate conversions, but we're going to roll it all into 1 conversion. We've done multi-step conversions before, where we use multiple conversion factors in one conversion. And so let's go ahead and get this done. Okay. All right. So we start out with, what do we start out with? Then we start out with 5.40 grams of hydrogen. Okay. What do we want to solve for? So on the other side of the arrow, we want to solve for grams of ammonia. Okay, so that's what we want to do. How do we get there? Okay, well, we got these conversion factors here. Okay, so the first conversion factor must cancel this unit out, grams of hydrogen. So of the 5 here that we have, which one can we use to get that done? Well, hopefully you recognize then that it's going to be this one right here, because that has grams of hydrogen in it and nothing else has grams of hydrogen in it. So the very first conversion factor we're going to use here then is going to be the molar mass of hydrogen. And how will we plug it in? We'll plug it in as 1 mole over 2 grams. Okay, so it's going to be 1 mole of hydrogen over 2 grams of hydrogen. Okay, and hopefully you see why, is that would allow us to cancel that unit with this unit right here, and so we end up with moles of hydrogen. So that means then we've used this one, we've already used this one, don't use it again. Okay, so the question then is, are we done with our conversion? No, because at this point here the unit is moles of hydrogen and we need to get to grams of hydrogen. We're not done. So the grams of ammonia, we're not done. Okay, so we need then another conversion factor that has moles of hydrogen. Well, this doesn't have it. Okay, this has it, this does not have it, and this has it as well. So of the 2 that we just pointed out here, the 3 to 2 or the 1 to 3, which one do you think we're going to use? Well, think about this. If we use this one here, okay, we use this one here. Remember, we have hydrogen here. We need to get to ammonia. Okay, this one has hydrogen in it, but it also has nitrogen. The calculation here does not involve nitrogen. it involves ammonia. So this is the only conversion factor here that has both hydrogen and ammonia, the mole ratio between those two. Okay, so the second conversion factor that we're going to plug in here then is this mole ratio here. And so hopefully you recognize then that we'll plug it in as 2 moles of ammonia over 3 moles of hydrogen. So 2 moles of NH3. And we have here 3 moles of hydrogen. And again, why do we do that? So we can cancel out that unit right there. So there it is. We've taken care of that. We are almost to the end here, but we're not quite. And so let's go ahead and once we have this done, we are done with that conversion factor. Okay, so don't use that again. And so we're almost done here. We have ammonia on the left-hand side of the arrow. We have ammonia on the right-hand side of the arrow, but the only problem is that we have moles of ammonia here. We need to get to grams of ammonia, and hopefully you recognize then that this conversion factor will get us to that end point. And so we'll plug that in as 17 grams of ammonia over 1 mole of ammonia. And that allows us to cancel out this unit here. And there it is. Now we have grams of ammonia on both sides. We know that the conversion's done. You punch in your numbers. Okay, punch in your numbers, and please be mindful of significant figures here. So you got 3 significant figures here. And then you get your answer then as being 30.6 grams of ammonia. So what does this tell us? This answer tells us then that if we start out with 5.4 grams of hydrogen, we will produce 30.6 grams of ammonia. Okay? And so that's what the stoichiometric calculation allows us to do. Okay? All right. Very good. So let's go ahead then, and let's go ahead, and I would like to ask you to do number 9 in your problem set. Okay. So take number 9 here. Take about 3 minutes to work out this problem. Okay. Now to do this problem here, remember, get the balanced equation first. Identify what you are starting with. Identify what they want you to solve for, and then get the conversion factors that you need. Okay. So we'll do all that again in just a moment. Take about 3 minutes. Get that done, and then we'll go over it together. Okay. Go ahead and get it done. All right. Well, let's go ahead and let's take a look at what we have here. First of all, let's write out the balanced equation. Okay, let's go ahead and write out the balanced equation for this. Okay, so the balanced equation, hopefully you got this. If not, again, you need to practice. So the balanced equation then would be 4 irons plus 3 oxygens, okay, to produce for us 2 iron Fe, iron 3 oxide. Okay. Okay, so that is the balanced equation. 4, 3, 2 will help us to balance this out. Okay, let's go ahead then. Let's write down what they give us and what they're asking us to solve for. Okay, so let's go ahead and do that. So they tell us then that we have 12 grams of iron. Okay, so if 12 grams of iron rust. Okay, they're telling us then that we start out with 12 grams of iron. Okay, so they're telling us that we have this much. Okay. And how many grams of rust are produced? This is rust rate. Iron 3 oxide is considered rust. And so what we want to solve for then is the amount of iron 3 oxide, okay, if we start out with 12 grams of iron. Okay. All right, so just like what we did yesterday, and I'll do this one more time today for this one, but hopefully I said after this problem, we don't have to write them all out again. Let's write out the mole ratios. Let's write out all of the mole ratios that we can get from this reaction. Okay, so hopefully everyone see 4 to 3. Okay, so 4 moles of iron, 3 moles of oxygen. Okay, so that's, and then again, take the reciprocal of that. Okay, how about 4 moles of iron and 2 moles of iron 3 oxide. Okay, as a second one, again, take the reciprocal of that one if we need to. And then finally, 3 moles of oxygen over 2 moles of iron 3 oxide, Fe2O3. Okay, all right, so those are the 3 mole ratios that we need, okay, that we may need. Okay, all right, so we have iron, we have the amount of iron, and then we want to solve for the iron 3 oxide. So those are the two components of this reaction that we're comparing. And so what we need then is we need the molar mass. Let's go ahead and find the molar masses. Molar mass of iron. Let's go ahead and do that first. This should be pretty simple because the molar mass of iron, we can get that straight from the periodic table. Okay, it's 56 grams, so it's going to be 56 grams of iron for every 1 mole of iron. Okay, so there it is. That's the molar mass of iron. And then we need the molar mass of iron 3 oxide, which we have to calculate for. Molar mass of Fe2O3. Okay, so if you calculate for that, you end up with 160 grams of iron 3 oxide for every 1 mole of iron 3 oxide. Okay, so it's been effectively what we've done. Essentially, what we've done here is we've just written out all of the conversion factors that we may need. Okay, all the conversion factors that we can obtain from this, the conversion factors that we may use in this calculation. Okay, so let's go ahead and let's write out the calculus. Let's carry it out. So we start out with 12 grams of iron, okay, and we want to solve for the mass of iron 3 oxide. Okay, so which conversion factor we need first? Well, we need the conversion factor that has grams of iron in it, and this is the only one that has it. Okay, so we'll go the molar mass of iron. So let's go ahead and plug it in as 1 mole of iron over 56 grams of iron. We plug it in that ways. Okay, so we take the reciprocal of this, we plug it in that ways. Mass, the grams of iron cancel out. Okay, right. The next conversion factor needs to take us from moles of iron to grams of iron 3 oxide. We don't have that, but we do have moles of iron to moles of iron 3 oxide. So we can go ahead and use this conversion factor right here. We can use this mole ratio, okay, in order to get this done. So hopefully you see then, we'll plug it in as 2 moles of iron 3 oxide over 4 moles of iron. Okay, that allows us to cancel this out. And then finally, to get us for moles of iron 3 oxide, the mass, grams of iron 3 oxide, we'll go ahead and we'll plug in this last conversion factor here of 160 grams of iron 3 oxide over 1 mole of iron 3 oxide. Whoops, sorry. All right. And that allows us to cancel that unit there. And then so we end up with grams of iron 3 oxide on both sides. We can go ahead and punch in all the numbers, and then our answer to 2 significant figures, 17 grams of iron Fe2O3. Okay, so again, what does this number tell us? What does this answer tell us here? It tells us then that if we start out with 12 grams of iron here, and we run everything to completion, we do everything perfectly, we have more than enough oxygen, we will produce 17 grams of iron 3 oxide. Okay, all right, very good. So make sure you practice this for tonight, okay, and then we'll combine, see if you have any more questions, but we need to continue on. Okay, so we'll practice more of these mass to mass conversions. Hopefully tomorrow I'll have a couple more. Well, we'll practice a few more tomorrow. And then, but you got to practice on your own. Okay, so practice on your own. But you have to continue on, and we can do other types of calculations that involve stoichiometry as well. We can do other conversions as well. And the main reason for this, then, folks, is because we know then that there is this relationship between the mole unit, and not only mass. That's what we took advantage of here in doing the mass to mass conversion. But we also know then that there's a relationship between moles and volume of a gas at STP, and moles and the number of particles, representative particles, which are the number of atoms and the number of molecules. And so let's just say hypothetically, we know the number of atoms or the molecules involved in a particular reaction. We can actually solve for it as well. Okay, I mean, it wouldn't be a practical thing to do in terms of carrying out the reaction, but it's something we can do because we know then what the relationship is between representative particles and moles, and that's Avogadro's number. And so we can do a number of different stoichiometric calculations based on what we know about the relation between mass, volume, and number of representative particles, how all those relate to the mole. We need to remember that in order to get these other calculations done. Okay, but if we remember that, then we can do calculations that involve other conversions as well. Okay, as long as we can get the balanced equation, as long as we remember those conversion factors and obtaining those conversion factors, we can get it done. Okay, and so with that said, then if we consider what we have here, and this is a reminder of what we did back in chapter 10, these are the relationships here between moles and particles, and there it is, Avogadro's number, moles and mass, we already used that, molar mass, and moles and volume, which is 22.4, and this is for gas at STP. Okay, and so you don't have to worry about this last conversion here, but you do need to remember the first three here. Okay, because we can then go ahead and work out a problem that involves other types of stoichiometric conversions. Okay, to get that done, then what do we need? We need to make sure first and foremost get a balanced equation. Always get that first. Okay, always get the balanced equation first. You want to, and this is basically what we've been doing anyway with all of the conversions we've been doing. Okay, so then go ahead and ask yourself, what is the starting unit? So identify that. Okay, then ask yourself, what do you want to solve for? What is the end unit? And these are questions you've been asking as you do these conversions anyway. And then finally, you want to make sure that you pick the correct conversion factors. You come up with the correct conversion factors to get you from start to finish. Okay, so basically, that's essentially what we want to do. And then you want to make sure you plug in these conversion factors correctly so that the units cancel out. Okay, and then at the end, multiply or divide all the numbers, get your numerical answer. Okay, so 6 steps. It seems like that's a lot, but you've done all these and you are capable of doing this already. Okay, so what we want to try to do then, and we'll pick up with this tomorrow. Okay, we're going to do these mass to particles calculations. Okay, so that means then if we start out with the mass of a particular compound in the reaction, can we find then the number of particles of a second compound or the second component of a reaction that's involved in this reaction? So the question is, can we do this calculation directly? And the answer, first of all, is no, we cannot. And so how do we go about doing it? Okay, so we'll pick up with this discussion tomorrow, and then work out a few problems involving this tomorrow as well. And then I also want to start out tomorrow with the practice of doing more of these mass-to-mass calculations, and then we're going to deal with this conversion here as well. Okay. All right, folks, very good. Please make sure you come by and get your questions answered if you have any questions, and then if not, I will see you tomorrow. Okay. Have a good day, folks.